Hello, everyone, and welcome to our webinar on bio-based polymers. I'm really glad that so many of you registered. And a few things in advance. We will record the webinar and are planning to upload it on YouTube. We will also disseminate the presentation slides afterwards. So I will write everyone an email afterwards with the link. And we will hear now 15 minutes presentations from 7 projects about bio-based plastics. And after each presentation, you will be able to ask questions. So please use the Q&A box for the questions, and we will try to answer them after each presentation. And yeah, we will have a short coffee break of about 25 minutes after the 4th presentation, and we will have a bit more time for questions after the presentations about the regulatory landscape. This is the 4th one. So because we thought that this topic might affect quite some of you, so we have 15 minutes of time for questions then. And yeah, you will find all the information also on the website. I hope you have the link. And I'm very grateful that the great speakers agreed to present their projects to us. And I'm very curious about their research. So María López Abelairas will begin with AFTERLIFE project. She is a team leader and research and development manager at Idener in Spain.
Okay, so thank you very much, Freya, for the nice introduction. So thank you very much to the audience for all for their interest in this workshop. So as Freya mentioned, I go to present the AFTERLIFE project. I don't know, Freya, can you confirm me if you can see my presentation now?
Yes, I can see it. Perfect.
Perfect, thank you. So yes, my name is María López. I come from the company Idener in Spain, and I'm the person in charge of the coordination and today of the presentation of the AFTERLIFE project. Similarly to the rest of the projects in this workshop, AFTERLIFE is found by the Bio-Based Industries Initiative of the ACE 2020 program. So what is the what is the purpose of the project? So the aim of AFTERLIFE is the development of a technology for the treatment of wastewater and for the valorization of the value of the compounds of interest that we can find in this wastewater. So for this, we have developed a first pretreatment step with the filtration cascade for the separation of the suspended solid in the wastewater. These solids are go into a process of extraction of the compounds of interest and purification. The rest of the organic matter after this extraction step is used for the in a fermentation as feedstock in a fermentation step for the production of volatile fatty acids. These volatile fatty acids are the feedstock for the production of PHA or polyhydroxyalkanoates, that are bacterial biopolymers, and these PHA are used as basis for the production of plastic products. Besides, we produce a stream of pure water that we can reuse in the process. So here you can see more details about the project. So the total duration of the project is 4 years. Well, actually, due to the COVID situation and the delays related to it, the duration is 4 years and a half. So the project started with 15 partners from 7 different countries. Here you can see the consortium. That is a combination of RTOs and SMEs of different countries that covers the complete value chain of the process, from the wastewater producers to the bioplastics compounders. So here you can see the link of the website of the project to see more detailed information. So we go more in detail in the process. So first, we collect wastewater, in this case from 3 different sources: from cheese production, from candies production, and from a company that processes the citric fruit for the production of essential oils and of juice. So the wastewater goes into a pretreatment that consists of a filtration cascade that use different membrane technologies for the separation of the suspended solids. These technologies include the microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. So the separated solids goes into a state of extraction of the compounds of interest, in this case mainly flavonoids and lemonoids that can be reused as food additives in the process. The rest of the separate solids goes into a fermentation step for the production of volatile fatty acids, a mixture of acetic, propionic, and butyric acids that are used as feedstock for the production of polyhydroxyalkanoates that are processing into plastic products. And the rest of the organic matter not converted into PHA are introduced in an anaerobic digestion step for the production of biogas that can be used as a source of energy for the process. So what are the expected impacts for this project? Well, first of all, we try to demonstrate that that AFTERLIFE is a good alternative to the current benchmarking technologies for the treatment of wastewater, with the production of high value-added compounds, and also with the reuse of 100% of the suspended solid in the wastewater. We also try to connect different clusters and different industries in the bio-based sector. For example, the production of bioplastics and the wastewater treatment management. We also try to contribute to the production of new bio-based consumer products, and also to boost the participation of the small and medium enterprises in the development, the exploitation, and the application of the technology. I would like to highlight this impact, that is the foundation of one new bio-based value chain and one new bio-based material, because this is the topic of the current workshop, and in our case is the production of bioplastic materials from the PHA produced from the wastewater. So we go to stop and to see what is the PHA. Probably many of you know that that PHA or polyhydroxyalkanoates are biopolymers formed by hydroxy acid monomeric units. So some bacteria are able to store this polymer inside. How they store this polymer? Well, they store the PHA in media with a high concentration of carbon and with the deficient concentration of another nutrient, for example, nitrogen or phosphorus. So these conditions provoke the carbon accumulation in the form of the PHA as a way to accumulate energy. We have a lot of different PHA, a wide range of PHA that can be produced, but we can differentiate 2 main types: the short chain length PHA with less than 5 carbons in the chain, and the medium chain length PHA with more than 6 carbons or more in the chain. In the case of the short chain length, we should remark the most common one, that are the PHB or polyhydroxybutyrate and the PHBP or polyhydroxybutyrate palette copolymer. This PHA has very interesting properties. For example, they are biodegradable. They can use as basis for the production of thermoplastic materials. They have resistance to the ultraviolet radiation, and they are also biocompatible. So it's possible to use them in a wide range of applications, from the development of plastics for packaging to medical devices. So how we produce PHA in Afterlife? So the first step, if you remember, was the production of the volatile fatty acids. So here we achieve good results in the conversion of the suspended solids separated from the wastewater for the conversion into volatile fatty acids. So now we have these volatile fatty acids, we use them for the production of PHA. We use two alternative bacterial processes for the production of this PHA. The first one is the use of pure cultures, that is single strains able to accumulate the polymer, or the use of bacterial consortium for the production of the PHA. Depending on the selected pathway for the production, we have developed fed-batch strategies in the case of the pure culture to increase the PHA accumulation, or fish farming strategies in the case of mixed culture. In both cases, we have produced PHA mainly two times, the P3HB or the PHBP. Also in both pathways, we have accumulation higher than 60% of PHA and yields higher than 0.6 grams of PHA per gram of substrate. So as you can see, the PHA has a lot of abundance for the application in industrial application, for the application in industry. So first is biodegradable in different conditions. Also can replace the current fossil-based plastics, so it implies a reduction in the greenhouse gases emissions. It's possible to produce PHA from different sources, even from waste, as in this case. So we don't have competition with the food chain, because we don't use sugars, for example, for the production. Also, PHA has excellent barrier properties, so it's something very good for the application of as a packaging material, but also has other properties, for example, printing, sealing, dyeing, and it's also possible to use it in or process it by different ways, for example, with injection molding, extrusion, or thermoforming. So even with this abundance, we have some technical challenge before the application of the PHA in the production of bioplastic materials. The first one is that the PHA has a very low thermal stability, because the polymer starts to degrade at 160 degrees. So it compromises the transformation into the industrial processing window. Also, PHA is a brittle polymer, so it has a very low ductility. So this limits the application in the flexible packaging sector. On the other hand, for the processing with thermoforming, we need to add some additives or other polymers to reduce the crystallinity of the PHA, and this way allow the processability, or to increase the processability of the polymer. So how we produce our bioplastics from PHA in Afterlife? We use the PHA produced in the bacterial process it to produce the PHA-based material and after that process this PHA-based material for the production of bio-based food trays, bio-based plastic bags, and also for the production of bio-based mulch fields. We also assess the compostability and biodegradability of the material, and also the recyclability to be reprocessing again for the production of new material. So how we deal with the limitations, with the technical limitations of the PHA? Well, in this case, we have followed different strategies. The first one was the use of cleans to increase the thermal stability of the material. Another is the use of elastomers, for example, thermoplastic polyurethane, to increase the ductility. And the final one, and the one with the best and the most promising properties, is the mixer with PLA, with polylactic acid, to increase the processability of the material. So here we are now ongoing in the environmental, technical, and social assessment of the technology. But in any case, I would like to show some initial results. So here you can see the CO2 emissions associated to the afterlife process. As you can see, the process is in a good situation to compete with other alternative technologies for the production of PHA from different sources, for example, sugars from corn or other organic waste. And also the impact is significantly lower than that of the fossil based materials, for example, the polyethylene. So just to sum up, it seems that it's possible to overcome the technical barriers associated to the use of the PHA as bio-based material, not only due to the developments in this project, but in previous ongoing projects with PHA. It's possible to use waste for the production of the PHA. So here we can increase this way the availability of the PHA. The use of PHA has a lot of techno-economic, environmental, and social benefits. For example, the reduction of the pollution associated to the conventional plastics, the use of waste for the production, and the reduction of the greenhouse gases emissions associated to the conventional plastics. And there is another point that we go to treat in another presentation in this workshop, that is about the regulation. We must assess how the regulation help or need to push the development of the PHA production technology to facilitate the entry in the market. So this is all from my side. So here you can see the link to the website again, and also my contact. And it will be glad to address your questions, or you can contact me in this email address. So thank you very much.
Thank you, Maria. We have two questions to you. The first one from Julia Belopuhova. She says, good afternoon, Maria. Please tell us if you have considered the total inputs and outputs of substances and energy, and what are the prospects?
Well, so thank you very much for the question. In fact, as I mentioned, we are now working in the final assessment about the environmental and the techno-economic perspective of the project. So here in this assessment, we go to consider, of course, all the inputs and all the outputs. For the moment, we see that the perspectives are good because we can, in fact, we can use most of the suspended solid that we recover from the wastewater, and it's possible to convert them into final products that we can use. And also in the part of the energy, we see that we are analyzing the main hotspots in the project, but taking into account that we are producing energy also in the process with the anaerobic digestion, the output, we hope that the output will be good.
Edward Slavinsky asks if it makes a difference which waste stream you use, which type of PHA you can produce, and which properties the PHA bioplastic will have.
Well, in fact, we saw that depending on the wastewater that we are using, the profile of the mixture of volatile fatty acids is different. So depending on this, also the nature of the PHA can vary a little bit, but not very dramatically, I got to say. So the project is quite stable, independently of the input stream.
Mm-hmm. Someone asks, what is the difference in PHA and PABT?
Well, PHBB is a kind of PHA, so it's a short chain PHA. So the PHBB is a copolymer of hydroxybutyric acid and hydroxyvaleric acid. Typically, the characteristics of the PHBB are the physical characteristics and the processability characteristics of the PHBB are more attractive in general than the PHB only. But yes, this is just a kind of PHA.
Mm-hmm. And you mentioned to have mixed PHA and PLA. Marianna Faraldi asks whether you can provide us more information. Did you mix the pellets before the extrusion?
Well, this is something, yes, probably we can discuss. You want to contact us, probably I can put you in contact with the partners that are in charge of the process of the polymer here, and probably they can share with you more about the process for the mixture of the PLA and the PHB.
Mm-hmm. There are quite a bit of a few questions. Please place your questions in the Q&A box, because otherwise I have to check two.
Yeah.
So,
yeah, probably Freya, if you want, I can't reply in the box, okay? To follow, or what do you think?
I would just, we have 3 minutes, so I would.
Okay, perfect.
Some of the questions. Compared to conventional plastics, the oxygen and water vapor barriers of PHAs are not so good. This is particularly problematic for food-related applications. Which strategies are you using to solve this? Well,
actually, the barrier properties are quite good in the case, at least, of the PHB. Other PHA, probably we have more problems with them about this, but in the case of the PHA, the barrier properties are quite good. In any case, as I mentioned, we need to apply different strategies to improve the physical properties, but due to other reasons, probably for the low processability, the problems with the of degradation in the processing window. So this is something that we are trying to address now in the project.
Stephanie Stute wants to know what productivity you achieve in your process in gram per liter and hour.
Well, now the data that we have are at lab scale. We are now scaling up the process, and we are waiting for the final results of a higher scale. But in the lab scale, the minimum and we achieve at least if I remember well, 1 gram per liter per hour of PHB production. But I have to check this again, but it's in this order, more or less.
Mm-hmm. What are the possible additives that are being used in order to improve processability of PHA?
Well, some of them can be the clays, because they allow to increase the processing window, increasing the thermal stability of the process. Another is the use of elastomers, for example, the TPU, as I mentioned in the presentation, to increase the ductility. and others are the combination with other biopolymers, for example, in the case of the PLA, to increase the processability of the polymer.
Mm-hmm. Okay, thank you, Maria, for answering all the questions.
Thank you very much.
Presentation. The next presentation is will be from Lidia García Quiles, and she has a very unstable connection, so she will say hi to you, but I will play her presentation as a video that we recorded beforehand.
Yeah, thank you very much, Freda. That's all what I wanted to say. That good afternoon to everybody. Thank you very much for staying here, and to the AFTERLIFE project and the Nova Institute for hosting this wonderful meeting. And basically just that I have some problems yet with the internet, but now I think it's a little bit more stable. But anyway, as I have prepared in advance, I prefer just to not have problems, and we have the time perfect to play it. And then for sure I will be here to read the question, answer the questions in the coming minutes or in the final discussion. And also that you have in the first slide my email, so that if anyone wants to contact for further details or whatever, we will be glad to answer directly or put in contact with the adequate person of the project. So having said that, I think you can play it. Thanks.
Okay, thank you, Lidia.
Good afternoon to everybody. My name is Lidia García, and I'm the research manager at the SME Tecnopackaging, partner of BioBarr project. First of all, I would like to thank the AFTERLIFE partnership for organizing this workshop and invite us to show the results of BioBarr. I hope you enjoy. In this presentation, I will show you the BioBarr concept, the problem to overcome, objectives and value chains created, the extraction of compounds for matrix and additives, formulation of the materials to produce the different filaments, prototypes building through 3D printing, and the validation of the prototypes. And finally, you can find at the end of the presentation our scientific publications. For the construction and automotive sectors, as well as other key industrial sectors in the European economy, need biopolymers to produce new bioplastics with excellent structural and functional properties while increasing the sustainability. When preparing the proposal, the only biopolymer commercially available was PLA for this type of 3D printing technologies. But this was only available and achievable in a moderate price for domestic kind of machines. Other very high-tech technology was used for prototyping in the aeronautical sector, such as bike or pig, but this was also too expensive. So there was a gap in between to obtain engineering plastics, bioplastics that could be able to withstand high temperatures and with good mechanical properties. In addition, we found that the aesthetical properties were not so much explored, and we could find there an opportunity to develop quite a broad gamut of different materials. Therefore, the main ambition of the BioBarr project was to develop polysaccharide-based engineering bioplastics that were sustainable and competitive in price. Where it's more, the functional properties were given through the addition of valuable active compounds derived from agricultural residues. FECOAM was providing the agricultural biomass. KTH was extracting and compatibilizing the polysaccharides with the commercial matrices. University of Alicante was extracting the different functional compounds. Then Celabor was acting as the piloting or upscaling plant for both developments from KTH and University of Alicante. University of Perugia was working in the formulations of the final materials and also in the LCA assessment. Then Nurel was providing the commercial matrices to which all these modifications were made, and Tecnopackaging was upscaling the final formulations, the final blends of the materials and producing the filaments. Then these filaments were tested by ITIP through fused filament fabrication 3D printing technology, and ITIP was also obtaining the final prototypes. Finally, Acciona was validating the construction prototype, which was mold, and Fiat was validating the final automotive prototypes, which were a dashboard fascia and the door trim. The expected properties of the BioBarr products were to obtain an increase in the mechanical properties of a 40%, specifically when dealing with bending, tensile strength, and fatigue, but also enhance the scratch resistance behavior. When we talk about thermal properties, the target was set out by the construction sector in achieving at least 140 degrees Celsius, which was key and strategical for the application, the mold. And finally, more focus in the automotive products were good requirements or key requirements to get broad color gamut, enhance the fastness of the natural colorants into the polymer, and also to be able to obtain different textures and even introduce a customized fragrance. For the extraction of natural dyes, biomordants, antimicrobials, and essential oils, microwave-assisted extraction, MAE, was used. This powerful technique let us obtain these bioactive compounds that were used as additives to the polymer matrix. From the lemon peels, two main different compounds were obtained. On the one hand, we were able to extract the essential oil to confer with an intense fragrance and also with antioxidant properties to the polymer. And also we were able to extract the yellow pigment powder. From the broccoli as well, using this MAE technology and with acetone and centrifugal partition chromatography, a dark green was extracted. From the pomegranate, two different products were obtained as well. In this case, from the areoles, an intense dark pink or red powder was obtained. And from the peels, the biomordant powder was as well extracted. This biomordant helps to improve the natural dye fastness of the color into the applied matrix. We could say even that the pomegranate was probably the most versatile agro-residue used, because by varying the pH when fixing this pigment, we were able to obtain a very broad gamut of different colors, from pinkish to grayish. Finally, the latest additive obtained came from the almond shell by milling through a micronizing process. Different diameter sizes were obtained and tested, trying to confer the final material with a woody-like natural aesthetical aspect. That previews were related to the functional molecules, and now the extraction of starch and arabinoxylants from corn residues was also carried out. In this case, subcritical water extraction was used as a green technology compared to conventional organic solvent extraction methods, because it used non-toxic green solvents, and in this case, just water was used. So with these technologies applied to large volume of vegetable matrices in continuous extraction processes, we could obtain the different polysaccharides that were used as part of the matrix, of the biopolymeric matrix in the project. And you can see there the biorefinery station of the labor partner, in this case, for the upscaling purposes. So in our case, starch was obtained and purified in order to be used as the main bio-based component, as I mentioned, and it was added to some polyamide polymeric matrix offered by Nural in this case, with the aim of reducing the oil-based content. Here in the BioBarr project, when we are talking about the polymeric matrices, some were used using the Einsia grays, which are polysaccharide-based, and we were contributing by introducing as well these arabinoxylans and these starches. But the key ones for the high-tech thermal properties were based on some polyamides. And there was a hard exercise of compatibilizing these polysaccharides, these starches and arabinoxylans with the polyamide-based materials. The minimum content of bio-based material in the most technical grades is of the 25%, and we were increasing this. The BioBarr materials were developed through an extrusion compounding process. The twin screw is comprised of small pieces called screw elements that are assembled in the shafts. In twin screw extruders, there are three main types of screw elements: the kneading blocks, reverse screws, and conveying screws, which basically permits to transport, mix, and control the searing. The screw profile is a very important factor in extrusion processes and affects significantly the transport of the materials in the extruder. In the BioBarr project, the development of color blends requires special expertise in combining these screw elements, feeder positions, and remaining time in order to obtain a well-dispersed blend, but avoiding at any time any burn or degradation of the material. However, the development of polyamide starch blends requires of a more complex technique called reactive extrusion, or REX. It describes a special process in extrusion technology in which individual components are bonded by a chemical reaction that occurs in situ during the melt processing. The chemical modification of polymers is carried out during the extrusion process by treating them with peroxides or by crafting molecules of different chemical nature. In this sense, three main steps were carried out. Firstly, the starch used in BioBarr was functionalized with an acylating agent. Then, the modified starch was predispersed in glycerol and a thermoplastic starch TPS was produced. And finally, the polyamide matrix was also activated via reactive extrusion with an anhydride and an initiator, typically using a peroxide. In this slide, you can see examples of different materials and blends obtained through the piloting process. From the lemon peels, you can see also a gray and a pink color based on the pomegranate, and also some filaments coming from the almond shells. Here in this picture, you can see the production of the filament spools. Basically, we were using kind of pilot lab, small scale spooling machine, in which it has a small extruder that melts the formulation that we wanted to obtain, and we are able to get the filament with the adequate diameter and the adequate properties for the 3D printing technology afterwards. And here you can see a list of the materials that we obtained based on the Einsia, which are the polysaccharide-based materials, and the different polyamide-based enhanced formulations in the project. Once we had the different filaments, we had to test it in the 3D printing process, and here you can see the machine used in BioBarr. Basically, we had to validate the different materials, upscale it, and obtain different specimens for further testing and validation, apart from the final prototypes. The machine was modified by coupling a cold laser and a heating system to the nozzles, so that we could better enhance the interaction between the different layers and even increase the mechanical properties of the final product itself. So this is a video of the construction of one piece for the automotive using BioBarr material, and the transparent platform is built with an auxiliary material that is removed afterwards. So for the automotive sector, 2 industrial parts have been manufactured through FFF processing, which was the fascia and the interior door trim. You can see the final pieces on the right, and the fascia has been divided in 4 parts using 4 different BioBarr materials so that we can show the different colors, fragrances, and textures obtained. So finally, for the automatic validation, the materials passes 3 climatic tests, then a flammability test, a fluid resistance using different chemicals that we could use to clean our car, and the light aging. The different materials passed all the tests. There was some kind of gaps regarding the fastness in the light aging, but it was not so bad due to the fact that we were not using at any time UV blocker additives that typically these parts use. So that would be the room for improvement of these materials anyway. For the construction sector, we built the 3D RTM mold mentioned before. In the pictures, you can see the concept, the original design, and the 3D printed mold with its aluminum case. To build the monolithic mold concept was a challenge in itself for the 3D printing technology. In this case, trying to solve the differences in the thermal expansion coefficient between the aluminum and the polymeric material was technically tricky. The result was quite successful, and about 40 joints were obtained. An epoxy resin with glass fiber was used for this purpose. So with all the joints that we were able to produce with the mold, then these were technically configured in the truss that you can see in the images, and they were tested under 35, 50, and 75 kilonewtons, applying the load 3 times, and no damages were observed. Thus, there was a structural integrity of the truss, and the piece produced with our mold was of very good quality indeed. And finally, you can find here our scientific publications regarding the extraction of bio-based molecules and the functionalization of bio-based molecules, as well as the designing of bio-based materials. Thank you very much for your attention, and I will be glad to answer any of your questions. Thanks.
Thank you very much, Frida. So this was the presentation. As I mentioned, if there is any question to answer, I will be glad to tell you.
Yeah, thank you, Lidia, for the nice presentation. Edward Slivinsky asks, can you maybe repeat what are the issues you are facing with PLA?
Okay, yeah, we mentioned PLA at the beginning of the presentation, yes, because we introduced a little bit the different materials that were used in 3D printing technologies, in particular in FFF, which is the one that we know, the one that is produced with the filament and that we may purchase, let's say, as a domestic level now, that technology. And at the beginning of the project, as bio-based material, okay, that was the only one that was known and that could be purchased at that moment. That was okay for producing your things at home, okay, but not for technical applications. And there was the opposite situation, which was quite cope with for aeronautical sector, with very, very high technical materials, such as the big one, for example, but those were really, really expensive. We are talking about the difference of a PLA reel for domestic issue of 20 euros the reel, more or less 1 kilo, or 150 grams, more or less, depending on the type of reel. respect to 500 euros, 1,000 euros for very, very specific and high-tech applications. So that was the issue at the beginning with the PLA. That was okay for some domestic tests, let's say, but there was a gap of materials, and there were no bio-based materials for a little bit more high-tech applications.
Mohammed Midani wants to thank you for your great presentation, and Sumit Lal asks, can you comment on mechanical properties of polysaccharides-based biocomposite and the composites being used traditionally in automobiles like ABS, etc.?
Yeah, basically regarding our materials and comparing to others like ABS, we were quite able to increase like 20 to 30% in mechanical properties with the enhance of the materials themselves. But also it was quite important, and I mentioned that we modify, or one of the partners I did modify the technology of FFF printing by introducing some heading that was working on the temperature and was working on the interface adhesion of the different layers in the activation. So the mechanical properties of our final products were enhanced by enhancing the compatibility of the different compounds of the blend on the one hand, but also physically with the technology itself. And we were able to reach that 40%. Compared to other materials like ABS, I could say that, for example, with the polyester-based ones, we were more or less in the same level of mechanical properties. But it is true that with the reactive extrusion and the polyamide-based ones, we were able to achieve quite much better properties, mechanically speaking, and also thermally speaking. We were quite impressed, for example, with when Fiat was making the flame test with the polyamide, with the pomegranate biomordants and the pomegranate colors, because it was even a self-extinguished material. So we achieved quite good properties in this sense. And regarding mechanical properties, they are comparable or even better, depending on the type of blend, because as I mentioned, we were working in two types of blends.
Okay, thank you, Lidia. I think maybe you can answer the other question in the chat, because we have to go further.
Okay.
So we are going on with Marianna Faraldi, project manager at Tecnoalimenti in Italy, and she will talk about the BioBarr project.
Hello.
Hello, Marianna.
So, let me know if you are able to see my presentation.
Yes, we see it.
Okay, thank you so much. Okay, good afternoon, and thank you so much for the invitation to this interesting workshop, for sharing the different experiences. So my name is Marianna Faraldi. I'm a project manager and senior researcher of Tecnoalimenti. Our headquarters is located in Milan, in Italy. So just a few words, Tecnoalimenti is a consortium of 31 food industrial members and the Italian Ministry of Research. So we play the role of research organization on one side, since we are no profit, but at the same time, we are led by the industry, the food industry. So the pillars of Tecnoalimenti, 40 years of experience since we were established in 1981. We are a no-profit consortium, as already said, so we act also into finance project in research and technology as a research and technology organization. We are guided, moved by the needs and requirements of our food industry members. And we are a lot focused on technologies. So we also have interest in technology transfer and technology scouting for our members. And we activated these activities through intercompanies innovation activities and through own research and innovation activities. So I'm here today for in my role as a project coordinator of BioBarr project, financed by BBIJU in the call 2016, so a lot of times ago. So the title is New Bio-Based Food Packaging Materials with Enhanced Barrier Properties. And it is a RIA, so a research and innovation action, with a TRL of 5, so very close to the research, but we tried to move a lot also close to the market where possible. So a duration of 4.5 years. In fact, we started in June 2017, and we will end in November 2021, so this year. 4 European countries involved: Italy, Spain, Denmark, and Finland. So I would like just to briefly summarize in which way this project was born. So our approach has been the approach which usually we use in our activities. So we started from industrial needs, and we arrived to the project idea and partnership. So starting from the needs collected by the food industry for innovation in food packaging, we realized that food companies was interested, also moved from the consumer's demands to more sustainable solutions in comparison to the fossil-based materials. And when we speak about sustainability, speak about improved production efficiency, always having in mind the environmental impact and the end of life of the material used. Then a longer shelf life of the product. Because if you consider that a product has a longer shelf life, it can reach new markets. So it means for an industry a major competitiveness, so the capability to enlarge its own market. And obviously, if I improve the duration of a product, a food product, I will reduce in some way the number of wastes which will go into the environment and which needs to be managed. And then the importance of functionality. So entering in more details in these 3 aspects, more sustainability means currently to move towards bio-based solutions, paying attention to the end of life. Longer shelf life means obviously to guarantee the sensory properties and the absence of unwanted microorganisms and molds. And obviously means that the product is fine under the quality and safety point of view. Barrier protection against oxygen, water vapor, dust, etc. is required by the industry, and the level of barrier protection depends obviously on the specific food product. When we speak about functionality, we refer to the capability to guarantee measure functions related to the food packaging. So we are referring to the capability of the final product to guarantee the containment, the protection of the food, communication towards the consumer, service content, and compliance to safety and regulations. So starting from the sustainability point of view, in 2016, we focused on the different possibilities, and we understood that for the best option in terms of bio-based and biodegradable, PLA, PHA, PBS, and starch blend were the best solutions. So we focused mainly on these. and in particular through having the possibility to meet an industry which was producing PHA, we decided to move towards polyhydroxyalkanoates. As already mentioned before by María López, whose presentation I appreciated a lot since we have some points in common, PHAs are 100% bio-based and 100% biodegradable, both in soil and water, fresh and seawater, so without forced biodegradability. We focused in particular in terms of PHA production towards agricultural byproducts, co-products and waste materials. And we tried to guarantee through the process a completely natural process, which is the fermentation one. The point is that, as already mentioned by Maria before, PHA as it is has some weak points for applications as flexible films for food packaging, in particular related to the low barrier properties. So we decided that the best solution was to functionalize this material, so to produce it and to functionalize, applying an additional thin layer of another material on top of the bio-based films in order to optimize the functional properties and increasing this weak point, but maintaining all its peculiarities and advantages in terms of biodegradability in particular. We decided from the very beginning that each innovative technological element to be included in this final final product, I mean the packaging solution, had to be integrated, guaranteeing at the end an entirely biodegradable solution. So, for summarizing the concept, we decided to start from food industrial wastes and co-products, in particular, in our case, from sugar beet molasses and juices, even if we know that PHA can be produced under different sources, as before mentioned by María López, for example, from wastewater. But we decided also moved from our shareholders and our food industrial industries to start from a problem, the problem of waste, which in this way will be valorized, and we can guarantee in some way a sort of circular economy. So from these sources, we were able to obtain PHA, so we recovered it, we purified the PHA, and through two different phases, first the obtainment of powder, and then the compounding phase for obtaining the pellets, we arrived to the extrusion phase for obtaining these flexible films. These flexible films were functionalized with different solutions, in particular the introduction of a very thin layer of aluminum and metallization on one side, and lamination with PLA on the other side. We introduced also the printing phase for arriving at the end to validate the new solution with an end user, in our case, a representative of the bakery sector, who is Corsini Bakery, located in Tuscany in Italy. So the main goal of BioBarr concerns the development of new bio-based and biodegradable food packaging materials by enhancing barrier functionalities to the biopolymer PHAs and by validating the new material in the food industry environment. So as a matter of fact, the expected outputs constitute the point of start for a technologically advanced, environmental, sustainable and reproducible food packaging generation. This is the partnership. So apart from Tecnoalimenti, with the project coordinator, we have another Italian partner, Ishimendue, with a converter. We have Kao Chemigraph, who is in charge for inks, new inks development.
Marianna,
Yeah.
Very sorry to interrupt you, but since I saw that you have a lot of slides left and it is already 14 o'clock, just a reminder that
Okay, so just for moving on, so the lines of development of the project, processability assessment and development of flexible films for food packaging applications, surface treatments, development of new bio-based and eco-friendly inks for printing, shelf life assessment, LCA, cost-benefit analysis, value chain analysis. So just to summarize, the results emerge in these years. So in terms of formulative development, different grades have been developed. We were able to reduce the costs through the improvements in the production lines and the use of wastes and co-products for producing biopolymers at competitive prices. In terms of processability and run ability, we demonstrated the compatibility of PHA both with blown extrusion equipment and co-extrusion coating and lamination line for obtaining flexible films. We understood that the PHA compound properties impact directly the setting of the used equipment. The process parameters of the equipment used must be adapted to the specific properties of the compound. It can be processed through the typical technologies of thermoplastics. It is able to be handled and rolled up and can be produced in different thicknesses. It is sealed and can be packed with an acceptable aesthetical appearance of the film. It is possible to look through even if it is not completely transparent. It is still a little bit milky. It is suitable for coating treatments and lamination. With or without corona pretreatment, this is something we are still investigation, and multi-layer solutions are feasible. Good printability, so the new inks developed inside BioBarr can be printed on the PHA materials. And in terms of analysis, we can confirm at the moment the general compliance of the new developed bio-based material in contact with food. So we have tested the overall and specific migration, compliance to biodegradability standards, but still in progress, the compostability assessment, some evaluations in terms of mechanical and barrier properties of the finished product, the printing process validation at industrial level, and the shelf life and acceptability studies, and LCA, CBA, and the value chain analysis. So for ending, new grades of PHA's biopolymers are being developed along the BioBarr project with improved performances that can expand the market for these materials in the packaging sector. It is experimenting their application in the food sector, and if we consider that packaging accounts for almost 50% of total packaging waste, the impact of such projects' outcomes for the future is evidently huge. In perspective, with the optimization of processes and with an adequate scale-up, thanks to a significant taking into consideration the investments needed, we can say that this kind of biopolymers can replace successfully traditional plastics already existing. even if some challenging are still under evaluation, but we think that the road is marked and upheld. So thank you for your attention.
Thank you a lot, Marianna, and also for speeding up.
I think I'm in time now. No.
Yeah, sadly, we missed some of your great pictures, but I think we got your project idea and progress. Maybe you can answer the questions in the box so that we can go on with the next presentation. In the question and answer box below, there's two.
How did you apply the coatings on your pH film?
Yeah, maybe you can do that in writing, and we will continue with the next presentation.
Yes, okay, thank you.
Thank you, Lidia, Marianna. The next one is our specialist on the regulatory landscape, and his name is Nicolas Haag from the Nova Institute in Germany, and he will try to give an insight into regulatory issues and also with a focus on bio-based polymers.
Thank you for the introduction. Let me just share my screen. All right, yeah. Welcome everyone. I would like to give you a brief overview of the Single-Use Plastics Directive, especially regarding biopolymers and also the general EU plastic strategy. And I would like to start with a picture that I think all of you are familiar with. So littered beaches are a great problem, and marine littering is a great problem globally. And as you can see on the picture, single-use plastics are a great part of this littering. And this is why the EU saw the urge to counteract these plastic littering problems. And in early 2018, the European Commission, adopted the EU plastic strategy. And from this EU plastic strategy, the Commission developed a proposal for a directive, which is called the Single-Use Plastics Directive. And this Single-Use Plastics Directive had been finalized and developed up until 2019 in the summer, when it entered into force. And subsequently, the European Commission adopted also the new Circular Economy Action Plan, which includes a lot of actions and directives, policy measures to counteract several littering and plastic problems, as well as other sustainability issues. But I will give you an overview of that in the after the Single-Use Plastics Directive in this presentation. So what's the background on the Single-Use Plastics Directive? The EU Commission has the Joint Research Center from the EU, and they told them to conduct a report on what items are actually found on EU beaches, how's the littering looking like in the EU, and this was conducted by the JRC, as I said, and this report shows the top marine beach litter items in Europe, and this is the initial background for the Single-Use Plastics Directive. This report found that 84% of marine litter is actually plastic, and 50% of this litter, so 50% of the 84%, are items that can be described as single-use plastic products. So in the figure, you can see, for example, cigarette butts and filters are some of these products, or cotton bud sticks, plastic caps and lids. Those are products that are aimed to be tackled by the Single-Use Plastics Directive. So what is this SUPD, the Single-Use Plastics Directive, all about? So the EU saw the urgency to counteract this plastic pollution, as I said, and as the JSC report found out, a large share of plastic pollution are actually single-use products. So the initial focus of the EU when tackling marine litter and the plastic problem were single-use plastic products, which is why the SUPD was the first action and directive from this EU plastic strategy. And the objective is to prevent and reduce the impact of certain plastics and plastic products on the environment, and also to promote the transition to a circular economy with an innovative and sustainable business model, and also, innovative and sustainable products and materials. So here you can see the implementation timeline of the Single-Use Plastics Directive. As I said, it was adopted in June 2019 by the EU when it entered into force. And after this successful adoption, the member states actually have 2 years to implement this directive or any directive into national law. So this is where we are headed right now. So between 2019 and 2020, clarification of open points took place, and also studies have been carried out. And in July 2020, the final version, including all the details and all the information necessary to implement it in national law, has started, which leaves us with the next big step in this timeline, which is the implementation in the member states, which must be finalized by July 2021, 2 years after the adoption, and then it becomes law. One thing that is important to note here is that the EU, the European Commission, wants to provide guidelines, implementation guidelines for the member states to help them implement the directive into national law. And these guidelines have been drafted a couple of times. The last draft is from December 2020, but the final guidelines are still delayed. And so how exactly the Single-Use Plastics Directive is going to be implemented into national law is still uncertain. So there are two crucial definitions in the directive. On the one hand, we have what is a single-use plastic product, and in the directive it is defined as a product that is made wholly or partly from plastic and that is not conceived, designed, or placed on the market to accomplish multiple trips or rotations by being returned to a producer for refill or to be reused for the same purpose for which it was conceived. So it is used only one single time. And the other definition is what is a plastic in this in the meaning of this directive. And a plastic is defined as a material consisting of a polymer which can function as a main structural component of final products, with the exception, and that is critical here, with the exception of natural polymers that have not been chemically modified. So this you can probably write down or have in mind when I go to the next slides, because this is very critical indeed. And these definitions of plastics cover also polymer-based rubber items and also bio-based and biodegradable plastics. So these are also falling into the scope of the SUPD. So as you can see, no exceptions for bio-based or biodegradable plastics. This is also very important takeaway from these definitions. What is a natural polymer? Since it is part of the definition of plastics, we have to talk about what is a natural polymer. So polymers, which are a result of a polymerization process that has taken place in nature, independently of the extraction process with which they have been extracted. That's the definition for a natural polymer. So, which would usually mean that, for example, a process like fermentation is some process that can occur in nature and therefore, should be a natural polymer. But in the latest guidelines, fermentation is not understood as a natural process, subsequently classifying PHAs, for example, as unnatural polymers, which means as plastic. Many scientists obviously disagree with this classification, and PHAs are widely seen as natural polymers, and since I'm sure you know, PHAs are produced by the same bacteria in nature and in industrial fermentation. So there's no logic behind this on why to have a distinguishment between PHAs stemming from natural processes and PHAs coming from industrial processes by the same fermentation process. So the ban for PHAs is quite a disaster for the young PHAs industry and all the projects, for example, like all the projects that are going to be presented today. But it's also a problem for paper and cellulose fiber industries that are actually looking for an alternative to polymer coating of their products. In the latest guidelines, we have the problem of viscose, cellophane, and lyocell, which usually also are considered a natural polymer. And in the first draft of the guidelines from September 2020, viscose and lyocell were not seen as a plastic, so they would not fall into the scope of the SUPD. However, in the latest guidelines draft from December 2020, these definitions have seen new interpretations, and these interpretations distinguished between chemically modified and chemically unmodified polymers. So this is another aspect that comes to the natural polymer aspect. So chemical modification is seen as covalent bonds that are broken or formed in the production process. So if covalent bonds are broken or formed, a chemical modification process took place. And on the other hand, if no covalent bonds are broken or formed in the production process, a product is chemically unmodified. And this resulted in the latest draft in a ban of viscose and cellophane, and lyocell remained approved in the latest SUPD draft. So this is also a huge point of discussion, and it was met with a lot of incomprehension and controversial discussions by stakeholders. And many of these saw these as not technically or scientifically justified. And a workshop in January, actually, between member states and the Commission, did not yield a plausible explanation for this change of mind. So what happens in the final draft or the final guidelines of the SUPD remains to be seen. And just an opinion on the consequences of viscose being called or being defined as plastic from a paper of Antje Pottas and Thomas Rosenau from Boco University. Why doing research if one of the purest celluloses available is classified as a plastic? This is basically what we can take away from this. And this leaves the consumers with non-science-based information about the materials that are being used, and also, possible wrong disposal of the product if there's viscose or cellophane in there, because they might be, disposed in plastic containers. And the other crucial part of the SUPD, besides the definitions in the guidelines, is which products actually fall in the scope of the SUPD. So what are single-use plastic products, and which are specifically named in the directive. And the SUPD sees several measures that have to be taken into account, and they are defined in the annex of the directive. Each part of the annex defines which products are covered by this measure. And in Annex Part A, for example, member states shall take the necessary measures to achieve an ambitious and sustained reduction in the consumption for cups and beverages and food containers. So these two products fall in the sustained reduction part of the SUPD. Then in Annex Part D, the products listed in there have to deal with clear marking on its packaging regarding appropriate waste management of the product and the presence of plastics in the product. So, for example, sanitary towels or wet wipes, if they contain a polymer that is considered a plastic in the SUPD, they have to clearly mark it on the packaging. which would, for example, in the case of wet wipes made from viscose in the current state, in the current draft of the guidelines, lead to wet wipes from viscose being called plastic, and would therefore possibly passively promote fossil-based wet wipes, since they are usually cheaper than the sustainable ones. So this is also a big problem in the current draft of the guidelines. And then we have two annex parts. On the one hand, the extended producer responsibility part, and also on the other hand, the measures to inform the consumers about reusable alternatives. And many of the products are falling into both of these annex parts. So food containers, packets and wrappers, beverage containers, tobacco products, wet wipes, balloons, those are all covered by both of these. I don't want to go into much detail here, since those are not the most strict measures in the SUPD. So because the strictest measure in the SUPD actually follows now is the prohibition to place a product on the market. So products that are going to be banned in the scope of the SUPD. This is pretty crucial, since these products are actually completely forbidden to be placed on the market. And there we're talking about balloon sticks, beverage stirrers, cotton bud sticks, cutlery, plates, straws, also cups for beverages made from expanded polystyrene, food containers and beverage containers also made of expanded polystyrene, and in general, every product made from oxo-degradable plastic will be banned in the SUPD when it's entering into national law in this summer. Yeah. So this is overall what the SUPD is all about. But this is not the only measure or directive that is going to tackle plastic usage in the EU. As I said, there's also the new Circular Economy Action Plan. And the new Circular Economy Action Plan from the EU also has some key actions in mind. For example, designing sustainable products, empowering consumers and public buyers, and also circularity in the production process. And as you can see, plastics are still a key value chain, even after the SUPD implementation. And you can also see some aspects that are going to be tackled as well. For example, toxics and plastics, or waste exports, and these aspects are then going to be tackled in specific actions and measures by the EU, which you they actually have a nice overview of these measures, which is quite a bit too big for one presentation here, but I tried to highlight the ones for you that actually deal with plastics. So the ones marked with the yellow arrow are actually dealing with plastic production or plastic disposal, or measures like this. So, for example, you see in 2021, it's planned to review the reinforcement and to reinforce the essential requirements for packaging and reduce overpackaging and packaging waste. And also, for example, policy frameworks for bio-based plastics and biodegradable and compostable plastics are planned for this year, and many other measures. But as you also can see, the only measure that has been implemented and actually finished by now is the one marked in green, a proposal for new regulatory framework for batteries. So you see that the EU is not quite in time with all these measures, and it remains to be seen how many of these are actually going to be finalized when it's expected in this in this overview. Thank you for your attention, and if you have any questions, I'm happy to answer them.
Thank you, Nicolas. We have no questions until now, so maybe we
if you don't have any questions by now, you can also just email me if you have some in the future. The email is in the presentation that you, I think, will get after the workshop. So feel free to contact me.
Mm-hmm. I think Ed de Jong says that there will be a question. He is asking, will bio-based be equal to recycled plastics?
This is actually hard to tell for the moment, because all the other measures besides single-use plastics are still to be developed, and how the how bio-based plastics are going to be dealt with is quite uncertain as of now. As I showed you in the overview of the new circular economy action plan, there's going to be a strategy especially for biodegradable and bioplastics. So what's going to be in there remains to be seen.
He adds that he is asking this in regards to content. I don't know if he means...
Maybe you could clarify this a little more.
Yeah, we have... in the meantime, we got a lot of questions. So Edward Slivinsky is asking, are all countries on track to implement the new legislation?
So they have to be on track, since it's mandatory to implement them in July, but they are all eagerly waiting on the final draft, on the final guidelines on how to implement the SUPD rules into national law. So how the implementation in each member state will go is quite unsure as of now.
Mm-hmm. And Ed added that he meant the required amount recycled. So
we'll
required recycled amount that has to be added, I think.
Mm-hmm. This one I'm actually not sure about. I'm sorry, I won't be able to give you more insights on this right now, but maybe we can discuss this via email.
Mm-hmm. Stephanie Stute says, many thanks for this nice and informative talk. Do you know why the EU is not listening to scientific knowledge? Why is the focus not more on biodegradability?
So this is the answer to this is layered. So, for example, the EU not only has sustainability in mind when discussing topics like this, there's also economic powers working, and other aspects that have to be taken into account when discussing policy measures. Of course, we are all coming from a scientific looking from a scientific point of view. So in our view, it should be more scientific, but that's sadly not always how it works. And regarding biodegradability, so in the EU actually has, for example, a waste framework directive, which defines the best end of life options for products, and biodegradability is actually not the best end of life option for products in the EU, because the EU prefers circularity and recycling and reusage of products. This is why biodegradability is not the main focus.
Tom says, good presentation. Then Howard Burwell asks, is agricultural plastic mulch film a single-use plastic?
No, it's not. It's only the products mentioned in the single-use plastics directive annex are going to be counted as a single-use plastic product for as of now. So the agricultural mulch films are covered by other policies.
Mm-hmm. A question from Pedro Cartaxo: is the role of bioplastics regarding the recycling goal and landfills restriction being considered as a contribution of the bioplastics in the circular economy?
Let me read it again. So
question is not clear, I think.
Yeah, I'm a little unsure of what I can say to this.
Just go further to.
So what I can say is that landfills are not going to be not going to be the best option in the EU waste handling. So since recycling is going to be the most preferable option here, yeah, I'm actually not sure how this can be accounted to the landfills restriction. I'm sorry.
Johan van der Poel, how are PHA companies involved in influencing to this legislation?
So from what I know, for example, the Go PHA association is trying to heavily influence the outcome of this guidelines and the SUPD implementation. But it's so the overall phase of having influence on the decisions is officially over, actually. So it's hard to actually influence the outcome of the guidelines in a bigger way. But what I know is that, for example, Go PHA is trying to influence the outcome where it can.
Claude Dong Van Lee asks, would a packaging intended product made of a blend of natural seaweed extractives be seen as plastic in the single-use plastic ban?
Yeah, this natural seaweed extractives, this is a very special question. So it's a very specific question. It's hard to answer because it actually remains. It actually is important to see how it is going to be defined, or how natural polymers are going to be defined in the final guidelines. So I'm not sure what the natural seaweed extractives are going to be composed of. But yeah, if you said it's a blend, so if you blend some other materials in there, it's like it's possible that it's seen as a plastic, but it's hard to have a general statement to this as of right now.
Peter Desiree, isn't landfill in the EU forbidden after 2035?
This might be true. Yeah, I'm not sure about that.
Yeah, someone is adding a comment. This is a good question. The EU Commission wants first to develop a test method for marine biodegradability. This is not ready now, and we hope to have it at the next review of SUPD in 2027, which is very late.
Yes, that's absolutely true.
Okay. So someone is asking whether we should add the single-use mouth mask into that list.
That's actually a pretty good question, since it's quite prominent now in these times. But yeah, maybe there might be some amendments in before it comes national law.
Dr. Amara Iguarta asks, could be biodegradable and compostable packaging the first option for food packaging?
As I said, the EU tries to focus on recyclability and circularity. So biodegradability is not the best option considered by the EU. But in some cases, this might be a good option as well. Yeah.
Abir Bulejuja, sorry for not pronouncing your name right, I think. Would a packaging based on modified cellulose and PLA, PHA, or bio-PBS will be considered as a plastic in single-use plastic?
This is heavily dependent on how the cellulose is modified. So, for example, in the current guidelines draft, there are two cellulose, modified celluloses specifically named, as I said, lyocell and viscose. And so the modification is defined by, at the moment, if covalent bonds are broken or formed. And if the cellulose is modified in this way, that covalent bonds are chemically modified with an organic acid. As you said, it would be chemically modified, and if it's chemically modified, it's forbidden. It's seen as a plastic.
Mm-hmm.
Yeah.
Okay, I think we answered the questions for now. So thank you a lot, really on time.
Great.
The next speaker is Michał Świeciński, project coordinator at Selena in Poland. And I don't know if I pronounced your name correctly.
Almost perfect. Świeciński. It's difficult. It's Polish one.
Okay. Yeah, he will present the project BioMotive to us.
Yes, and together with Bartosz Ziółkowski, who is our R&D expert, and will present you the details, I hope, most interesting, in fact. So my part will be just the introduction and just few words about BioMotive as such.
Okay.
Our project concept is to create bio-based polyurethanes and fibers for the automotive industry with increased environmental sustainability. And we have 3 projects as a result of our products: textiles, seat foams, and cockpit components. However, not only products will have as a result, but also 5 installations ready to start, ready for production of bio-based products. So this is not only project dedicated for R&D, but also some implementation in the industrial scale. And we are talking about huge project because we have 16 partners out of 8 European countries. We started in 2017, and this year in November will be the closing of the project. So we still have few months to finish the project. Total cost is more than 15 million euro, and which is also important, with additional investment from private sector around 4.5 million euro. Long list of partners which create consortium. Me and Bartosz represent Selena, who is a leader, coordinator of the project, and we are responsible generally for development and production of bio-based TPU and 2K PU foams. But we have also on board some representatives of automotive sector like Mayer or Intap, so Polish company which is dealing with construction of special vehicles like ambulances, for example. And we have also on board Metsä, the Finnish partner responsible for production of regenerated cellulose fibers and wood pulp. We have also Novamont, responsible for bio-based building blocks and vegetable oils, and also some representatives of scientific units like ICSO from Poland, responsible for development of bio-based non-acylonide polyurethane, and also university in Pisa, or companies responsible for another scope of activities, like for example RINA, responsible for certification, or Cartif from Spain, responsible for LCA analysis. The most important goal of the project is demonstrating on the industrial level, industrial scale, production of innovative, advanced bio-based materials As I mentioned before, we focus on the thermoplastic polyurethanes, two components, thermoset pollutant foams, and regenerated fibers. What is interesting, we cover the entire value chain, starting from bio-based raw materials and then bio-based polymers application into specific interior parts of the vehicle. But as a result of the project, we think also about another application, not only dedicated for automotive sector. And of course, we also check environmental impact. As I mentioned, we did LCA analysis, and some results will be presented by Bartosz in the final part of the presentation in the conclusion.
Thanks, Michał.
And right now I step my part and Bartosz will present you some interesting details.
Yes, just hold on, I'll switch to my screen. Okay, I hope you can see the slides.
Yes.
Yes. Okay, good afternoon, ladies and gentlemen. As Michał introduced, my name is Bartosz Żółkowski, and I'm the technical expert in BioMotive project. So what you can see here is a general flow chart of the materials and of the materials that are being used, produced, and transformed in BioMotive project. So from the left, we will have, for example, wood pulp that is being produced and transformed by Metsä Fibers. We have cardoon plants that are being grown and processed by Novamont. We have fructose and other vegetable oils. So the Novamont company builds plants that harvest the cardoon seeds and transform them into oil. From this oil, they degenerate the fine chemicals such as bioazelaic acid, and they make also biobutanediol from the sugars. So these fine chemicals then go to the middle stage of the project. Selena is responsible for that part of the project, where we transform these fine chemicals into intermediates. We perform chemical synthesis, we design these reactions, we optimize them and develop formulations for these intermediates. And these are biopolyester polyols and bioprepolymers. Then we use these prepolymers and polyols to develop formulations of two-component foams for car seating and thermoplastic polyurethane for the cockpit parts. Then these materials are being transferred to the other companies in the consortium that deal with making the car seat foams and cockpit parts by injection molding, and as well as textiles for these seats. I'm not going to cover all of these arrows that you see here. I'm just going to go through the most important two materials and show you a bit of results. So in principle, you have the cardoon seeds here. They are being pressed to generate the oil. And then because oils, as you probably know, are composed of fatty acid triglycerides. And these fatty acid chains have double bonds. So you can actually chemically hydroxylate them and then break them where the double bonds were. So you're being left with decarboxylic acid triglycerides. If you then hydrolyze them, you end up with a mixture of different decarboxylic acids. If you separate them, isolate them, and purify them, you can get a decarboxylic acid that has 9 carbons in the structure, and this is azelaic acid, and this is what Novamont is producing within this project. Also, when you take a soup consisting of sugars, add some special microorganisms and mineral salts, you can carry out a fermentation in specially designed reactors. And during this fermentation, these microorganisms generate 1,4-butanediol. And then, of course, you can take this broth, you can filter it, evaporate it, and distill biobutanediol from this. And you can also use the dead microorganisms and off gases to burn them and to power your installation. So this is the system that Novamont is using. It's actually quite efficient. So these are two main components of BioMotive project, the bioazelaic acid and bio 1,4-butanediol. So here you can see our small glass reactor in the lab where we combine these bio materials with other petrochemical molecules. We had to do this in order to develop these prepolymers, polyol molecules, to have specific properties, because different applications in automotive, such as foams or thermoplastic urethanes, require slightly different properties from the intermediates. So overall, after many iterations and experiments, we developed two different polyols. One that is targeted and tailored for two-component foams and prepolymers, the other one for the thermoplastic urethanes. The first one was designed for car seat foams has 100% biocarbon content, and the polyol for TPU has 71% biocarbon content. The difference in biocarbon content is due to the other molecules that we had to add in order to obtain the desired properties of the polyol. So when you take the first polyol, the one for two-component foams, and mix it with a bunch of other different chemicals and combine it with isocyanate, you can have something like this on the left. This is a mold for the headrest, a car headrest. You mix all the chemicals together, you pour it in the mold, close the mold, wait 4 minutes, and after 4 minutes you can take out a headrest like this. And on the right you can see the major car seating parts completed, just in the same way as you see the headrest over here. We've managed to develop a formulation based on our biopolyols that gives a 60% biocarbon content within the foam. But of course, if you use cellulose fiber textiles to support the foam, to cover it with the foam with these fibers, you can get even higher. You can go even higher with the bio content. As for the TPU, on the right side on the video, you see two components of the TPU, thermoplastic urethane, being fed into the extruder. The extruder has two screws inside that are mixing those two components, allowing the reaction to happen. And after 1 meter in the extruder, you can already see a wire that it's already a reacted plastic, polyurethane. The wire is being drawn through water to cool it, and then it's going into the granulator where the knives cut it into these small granules you can see on the left over here. And one of the final formulations of our TPU has 67% of biocarbon content. This TPU has been sent to Meyer, which aims to inject such as cockpit parts, as you can see in the red square. The 3D design of the part is in the middle, but for now they tried more simpler geometries to optimize the injection conditions. So you can see on the right here that our bio TPU is able to be injected in these simpler molds. Now they are actually trying to inject it in these more complex parts. Apart from the lab scale, as Michał mentioned, we were supposed to design and build two installations within Selena. One was the polyester production plant, so we did it. We have the reactor capable of making 5 tons of biopolyols per shift. And here in the drawing on the left, you see an extruder. The orange thing is the engine. Here on the left, the screws are hidden, and on the above you see the dosing units for the raw materials. So this is an extruder that can produce 250 kilograms per hour of TPU. And on the right, you can see the trial test. This is not the bio TPU yet. This is just a standard petrochemical formulation of TPU, but we were testing the throughput and the granulator efficiency. So this was successful. So in the upcoming weeks, we will be testing the bio TPU formulation on this extruder. At the same time, because the TPUs and foams that we make are bio, but they are bio-based, that doesn't mean that they are biodegradable. This is same type of plastic as a normal TPU. The carbon's coming from natural resources, but it's still not, you know, digestible by microorganisms. So within the project, we also had a work package dealing with recycling. So we've collected some of the TPU scraps throughout the project. We milled them and injected them into these shapes. The blue shapes are sealant applicators that are normally sold by our company. When you apply tiles in your bathroom and you put some silicone in between the spaces, you use it to smoothen the silicone. So we use the same manufacturing plant and same injection molds that we normally use for these applicators. We injected the granulated bio-TPU scraps from BioMotive, and we were quite successful in producing such applicators, validating the assumption that, you know, you can recycle this TPU. The last topic is the LCA, the life cycle analysis. We also have a company within the consortium that's professionally dealing with such things. And what is a really nice result is that after they analyzed our bio-TPU recipes, as you can see, they calculated that the raw materials transport for these TPU recipes has a decreased global warming potential, and this decreases by 76%. So that's actually quite impressive that the bio-TPU that we developed has such an impact. So these are the major findings up until now. We still have several months within the project, so hopefully we will finish on time. I'm pretty sure that we will. So yes, if you have any questions, please feel free to ask within the chat or maybe after the meeting. So thank you.
Thank you, Bartosz and Michał. You were perfectly on time. So until now, not one question, but maybe they will come.
Yeah.
Because I think, yeah, you had a very interesting presentation. Timothy
Thanks.
Abraham asks, how do the costs compare with Petrol Pu?
Well, the costs. Unfortunately, the TPU is more expensive, but that's due to the scale of the raw material production. So because these are all demo plants, small scale demo plants. I mean, the effect of scale is so that it's still more expensive.
Sure. Did you test your material on any automotive component? Is it applicable for serial production?
Well, this is what María is testing. And together with María, as I showed you, these complex cockpit parts, they will try this on their production machines. So we will know at the end of the project, but as we speak, they are injecting it into the molds. And of course, we still need to optimize the process conditions and some additives to help, you know, with the smooth production. But it is possible. It still needs optimizing, but it has been done in the production scenario. So we're quite close to that.
And did you test the applicators that you showed us?
Oh, well, not in my bathroom, only in the lab.
Okay, but they have the right.
Yes, they're perfectly fine.
Lieve Hoflack asks, will the products be further developed for commercialization?
Well, BioMotive projects aims at demonstrating the production possibility as such. But so the commercialization would be post-project actions. So it is foreseen in the documents, but since we are not obliged to commercialize it, this is something that we will think of after the project with our consultants. Yeah.
Okay, no further questions at the moment, but to all the participants, you can also ask questions during the other presentations, and we will have more time for questions at the end.
Great.
So thank you, Bartosz.
Thank you.
The next presentation is from Dr. Amaya Igartua from Tecniquer in Spain, and she is presenting the project BioSmart. Amaya, are you there?
Yes,
Okay, good.
I will share the screen.
Mm-hmm.
Can you see now?
Yes, I see it. Yeah.
Okay. I go to present you. I am Amaya Garto from the Research Institution Tecniquer, and I am coordinated the BioSmart project that is related with biomaterials for smart food packaging. In the project, part is a project financed by BBI, BioBarr Industries Consortium, and the European Commission. And the participants are Tecniquer as coordinator, Idener, University of Reading, TechSense, Lille, Propa Group, RISE, Lipofabrik, WIPAC, University of Fribourg, GEA. And also we have an advisory board, including Naturwash, supplier raw material, GEA Food, also Unilever and Eroski. Sorry. First of all, I will explain what is the problem that we are facing out. In Europe, 88 million tons of food are wasted each year. This is equivalent to the 20% of the food produced in Europe. Worldwide, this corresponds to 1.3 billion tons, and in the world there are 820 million of people that have not enough food to eat. Then the overall objective of BioSmart project is to increase food shelf life in food packaging. Then we would like to avoid that the more than 50% of the food is lost in the food chain. We would like to reduce that. And also, since the food residues go to the way, and this represents, yes?
Quickly, could you just start the presentation again so that we see the, no, just below on the, start the presentation so that we see the big picture.
Yes, but I had troubles with the big picture, and I moved to this presentation mode. That's why. If I can try again, but just is to try to avoid any problem. Okay. Then you see better like this. Okay.
Yes, perfect. Thank you.
Then the actual package that is normally light, high performance, and have multi-layer, and in some cases it's difficult to recycle due to complexity of the packaging. In BioSmart, we introduce compostable or recyclable packaging from natural resources with high mechanical performance and with enough barrier to accomplish the needs of the food. Then the project addresses all the food chain of the products in the design phase. That means that in order to define the BioSmart project, the polymer manufacturer, the converter, the brand owner, the retailer, the consumer, and recycling has been taken into account in the moment of the design phase. Then the partnership, we have partners from Europe, that as we highlight different parts of Europe, and the partners are those that are really developing the packaging. But we have the advisory board that is a consultory body in terms of address the needs of what the research is being done in order to try to go in a pathway that after will facilitate the exploitation of the result of the project. In the development phase, we try to achieve TRL 5, starting from TRL 3, and we address packaging manufacturing with materials from bio-based. And we address biopolymers, PLA, PE, barrier coatings, hydrophobic surface, thermal regulation, antioxidant, antifungal, and antimicrobial based lipopeptides to also increase food cell life inside the packaging, and sensor indicating the food quality. That means that we monitor the gases within the packaging in order to detect when the food is losing their properties. Also, mechanical properties of the PLA has been improved, including biocomposite with nanoclays. It has been introducing this functionality in different demonstrators, and also in order to reduce the environmental impact when increasing food cell life. And we have also developed an application in order to define the materials functionality, the performance, and the commercial needs within the packaging. Then this is the example of BioSmart packaging, in which you show a sensor in the transparent film, top film, that is the sensor for detecting oxygen, CO2, and also volatile amines. As has been highlighted, has been reinforcing mechanical properties of the packaging using nanoclays, also including antimicrobial properties, depositing a layer with lipopeptides that are fixed in the surface using cold atmospheric plasma, and also different barrier coatings for oxygen, for water, and ultraviolet that will be explained later, and including also thermal regulation. Then we have been implementing the PLA with nanoclays. This is a patent from Idener, is partner in the project, and we have applied this PLA with nanoclays using a twin extruder, using a 3-step extrusion process, co-extrusion in line, and using PLA, the PLA with nanoclays, and also PLA sealing layer. As a result of this structure, we have increasing the young modulus by 20%, the elongation to fracture by 25% in sheet, and 70% in film. And it is possible to keep thermal properties, improving permeability between 20 and 30%. Concerning the barriers to water and oxygen, is also the nanoclays has been used in the PLA in the trays as a compounding, and also as a layer film in order to improve the barrier properties. And it has been possible to reduce 95% the oxygen transmission rate, and reduce 15% the water transmission rate. Concerning ultraviolet barrier, it has been achieved using thin oxide nanoparticles, applying soil gel coatings, and it's possible also to apply by spray. Concerning the antimicrobial properties, this has been achieved by immobilization by plasma of the lipopeptides in the packaging. The technology uses called atmospheric plasma, and using a precursor of a specific gas and chemical link to the surface, it's possible to attach the surfactant, the microsubtilene, and this niacin. These have different properties, and biosurfactant, antibiofilm, antiviral, antifungal, or antibacterial properties. And then one of the issues that we face is how to monitor the linkage of the lipopeptides into the surface using plasma. And this has been monitored using measuring the contact angle that is normally reduced, and also monitoring with infrared spectra. Another technology that has been used also to modify the surface is the replication using physical nanostructuring of the flexible surface in order to confer a surface geometry that are able to reduce or decrease the proliferation of the bacteria. We have observed that it's practically possible to achieve super hydrophobic surface with very high contact angles using this process. Another way to achieve functionality is to encapsulate the bio-based packaging with phase change material. This allows the thermoregulation of the packaging, increasing the time where you can keep a temperature between -5 to 10 degrees. We have used vegetable oils to achieve this, and these vegetable oils allows to keep constant the temperature when is transforming the phase. And it has been achieved by organic encapsulation or inorganic encapsulation. Being the inorganic encapsulation have a higher capacity of keeping the temperature constant. Another technology that has been implemented is the sensor that can be applied manually or automatically in order to detect the quantity of oxygen inside the packaging. The sensor absorbs LED light and is detected also the wavelength that emits the sensor inside the MAP packaging. Is modified atmosphere packaging, and with this sensor it's possible to measure the concentration of oxygen inside the packaging. Is EFSA approved, and also this sensor has been labeled by Solar Impulse recently. During the BioSmart project, and this sensor is already applied for 100% control in line. It's also possible to avoid the thrown away the food packaging during the production step. But in BioSmart project, this technology has also been applied to develop CO2 sensor. Trials in GEA machine is ongoing, And also volatile amines is with a manual application are developed and it is in a prototype scale. Additionally, it has been developed by Fribourg application in order to calculate the cost of the packaging in order to define at the design phase of the packaging which material, the dimension of the packaging, and how this will affect in the cost. It is a software tool in which it's possible to implement the different thickness of the layers, and with that it's possible to predict the transmission rate and also to calculate the cost. It is possible to introduce private data here. There are in this moment implemented some public data, but it's also possible to implement private data. And then as conclusion, different technologies are being developed to give functionality of the bio-based packaging to increase food cell life, including copolymer-based biomass, PLA with nanoclays, lipopeptides with antifungal properties, for example, texture surface with super hydrophobic properties, barrier coating for oxygen, water, and ultraviolet, thermoregulation, gas sensor, and the application to analyze the cost to introduce technologies in the market in the right moment. Preparation of functional prototypes and underway, and also the possibility to evaluate from consumer point of view the quality of the packaging. And the market is very big since processed food market consists in more than 46 billion euro. And okay, I will, if you have any doubt, please let us know. You have the contact details, and thank you very much for your interest.
Thank you for your presentation, Amaya. We have no questions at the moment. Yeah, but maybe we have, will you be there for the final discussion?
Okay, thank you.
Maybe you can answer questions later. And we can go on with the presentation of the project preference. Dr. Ette Jong will present it, and here's I know we have a question for you, Amaya. From Balamurugan Venkatesan, what is the cost of nanoclay and what percentage to add PLA?
Okay, this is a development from Idener. The quantity of nanoclays, we have tested different quantities, but I prefer that this will be answered by email later on. He can drop an email in order to, and I will contact Idener to provide this information.
Okay, maybe I can share the speakers' emails with the participants if everyone agrees. Okay, so then Ed, it's your turn.
Today about the preference project. Preference stands for from bio-based feedstocks via diacids to advanced bio-based materials with a preference for polyethylene furanoate. So this is an BBI flagship project. So we are talking here really of bringing a technology from TRL7 to TRL8. So the issues which I will discuss will be slightly different than, for example, in RIAs or in demonstration projects. Can I have the next slide? So I think what has become clear, I think overall in this workshop today is that not only Avantium, but I think also the European Union really wants to go from a linear economy to a circular economy, and at the same time also go from carbon below the ground to carbon above the ground. And that means that requirements there is really that we make materials which are recyclable, and also materials which can be produced or from biomass or from CO2, because that are the only two renewable carbon sources we have available. Now, the preference project is really talking about the use of biomass. On the next slide, please. That gives a bit the background on Avantium in this technology. Avantium is a technology company in existence since 20 years, and we want to create disruptive technologies together with partners, and to make renewable as well as circular product, as well as in a safe environment. On the next slide. We see that we have at the moment 3 business units. One is really doing high throughput analysis for the chemical and petrochemical industry. That is basically the foundation of our research and capabilities. But the major emphasis nowadays is on producing renewable polymers and renewable chemistries. Today we will discuss mainly the renewable polymers as exemplified in preference, but also we have technologies to produce sugars and to convert sugars into, for example, glycols. On the next slide, you see basically the state of where we are, and we have technologies in the lab stage, in the pilot plant stage, as well as in the commercial stage. I think over time we learned really to be able to license technology, or to really have partners convinced that your technology is viable. You have to go at least to pilot plant stage, and quite often you have to go already to the smallest commercial stage to show partners what is possible, but also to produce enough materials to do the accurate market assessment. So going back to the different technologies we are having. So today we're talking about the so-called ICSI technology on converting Fdca and monoethylene glycol into PEF. In addition, we have a RAY technology, which is making glycols out of industrial sugars via hydrogenolysis. And we also have a technology to liberate sugars from woody biomass, because we think on the longer term that is certainly a necessary component in the bioeconomy. On the next slide, we have a kind of overview on the PEF applications, and I think that is an important aspect for people who are part of this game, is that initially you quite often need higher value applications, because the first scaling up step is quite often resulting in more expensive product, because the scale is smaller, because the optimizations which are potentially possible you are not really doing in your plant. And to do so, it is really important that you select some high value applications. And so with PEF we have also done that, and I think these are the 3 main examples. I will come back to the why a bit later. On the next slide, we have one key aspect, I think, in coming up with a disruptive technology, and I think that is that you need to add something more than just that it is bio-based, or that it is much more sustainable. for example, in relation to greenhouse gas savings, but that you really have a technical property what is superior to the incumbent properties. Now, PEF resembles to a major extent the well-known polyester PET, but it has surprisingly some very beneficial characteristics. And some of the important ones are mentioned here in the bottom left, and that are actually the barrier properties of PEF. So both oxygen and CO2, and to a lesser extent water, are much less permeable through a PEF layer compared to a PET layer. And that really opens possibilities in a wide range of applications, because you can go to light weighting, you can increase the shelf life, and by increasing the shelf life, of course, you reduce, for example, food waste, what has a very significant effect on greenhouse gas savings. Because I mean, you can imagine that if you save 10% of the meat, what you have to throw out because you have a better packaging, then you have already a very substantial reduction in food waste. In addition to the barrier properties, also the mechanical properties and the heat resistance of PEF is superior to PET. And that means that even if initially PEF is more expensive than PET, I mean, you can still create a place on the market, because basically you are not directly competing with PET, but actually you're more competing with other solutions as polyamides, which are used sometimes as a barrier property. So I think that is one of the takeaways I want to give the people here, is that, I mean, if your bio-based product does not contain properties which are superior to the incumbent, I mean, we think if you really want to scale up these kind of processes. The next slide. Another thing what I said already in beginning is that you have to look at the end of life of your material. So can you recycle your material, and have you proven that you can recycle? So I think we have done a lot of work also in that respect. I hope that my phone stops now. I put it off. Can you recycle the material? And in addition, also you have to look into what happens with your material when it ends up in nature. Is it more biodegradable than the incumbent, or is it less biodegradable than the incumbent? Because we all know that plastic waste, and certainly also microplastics, will become a very major issue in the future. So if we look now into the preference project, and what I said was already that it is a FlexCheck project. So its primary goal is really the engineering and building of a FlexCheck plant for the production of purified Fdca. And that is well on the way. But also to make that happen, I mean, we have to demonstrate and validate bio-based materials in end-user applications. And so therefore we established quite some partners in the value chain, what I will show in the next slide, who can help us validate those kind of materials. Now, I mean, of course, you have to be confident that you can commercialize those bio-based products. So that also asks for quite some attention. I think Also, the environmental and socioeconomic performance of the developed products is an important aspect, and so also doing LCA work is an important aspect of the preference project. And in this case, Nova Institute has been very important in also assist us in that part. So this is now, these are the main partners of the preference project. We have a feedstock supplier in here, materials. We have an engineering partner, Worley, who will do the, who has done already the front-end engineering and design, and we will start now soon with the EPC phase. And we have converters who can convert the polymer into different kind of products. And we have a couple of brand owners enclosed. I missed, oh, sorry, I think I missed Nestle here. Sorry, I did a mistake here. I have to add Nestle. So we have Lego, Gabony, Carlsberg, Henkel, and Nestle as brand owners. Most of them are really looking into PEF. Henkel is also looking for FDCA applications, and Gabony is looking for some of the side products valorization. In addition, we have Spinverse and Nova Institute who, for example, help us with the dissemination and the administrative aspects, as well as what I already mentioned before, the whole life cycle analysis of the process. On the next slide, we see then how we build up the project, and I think in a way it is maybe rather typical compared to a traditional project. But the thing, of course, is that quite often there are not too many partners involved. So for the work package 1, what looks at the production of the feedstock fructose, only Terios and Avantium are involved. While for the work package 3, 4, and 5, who are actually engineering and building the different unit operations of the plant, only Worley and Avantium are involved. And it's the same is the case in work package 7, that the different application developments are in general bilateral, trilateral affairs between Avantium, a converter, and an end user. And I think what is also, I think, quite illustrative in this kind of project is that the goals are really also already to have that much proof of the demonstrators that conditional offtake agreements can be signed during the project. So we are really very close to the marketplace with the partners, and of course that is really important because yeah, of course the investment in this kind of plants is already over 100 million euros. So I mean, you really need to be aware that all aspects of the value chain are addressed. I mean, I didn't mention it here, but also part of the project is also really to make sure that you comply to the REACH and the food safety acceptance regulations, and but also that is all in place. On the next slide, you see a picture of the plant, but it has been developed together with Worley. At the moment, the area is made ready for groundbreaking. So some ground has been brought up, and that is now stabilizing, but we are ready to go for building. On the next slide, I give you some background on the information materials we have prepared. So together with Nova, I mean, we have some brochures and roll-up banners, etc. And over the coming time, this will be actively renewed and extended. I mean, the same is also with external communications. I mean, we do quite a few press releases, newsletters, social media, etc. to update everybody on the status of the project. I can also refer to a video. It was a little bit too long to already play here, but on this link you can find a video explaining a bit more the technological background of the preference project. And yeah, coming back to the business strategy, I mean, I already indicated that earlier. I think it is very important that you have applications with superior performance, and I think also there, I think it is to identify those applications. I mean, it is really important to be in connection with converters and brand owners, because I think certainly for us, I mean, initially we didn't really know what are the issues, where can our material be of added value, and if you are not in discussions with brand owners and with converters, for example, yeah, it's also very difficult for you to really yeah, come with good propositions to people. And just by talking and discussing things, I mean, over time we came to know what are really added value applications, but also we learned much better which technical thresholds we had to make them. Yes, I mean, for each application, different aspects are important. I mean, sometimes it is color, sometimes it is strength, sometimes it is elongation at break, etc., etc. And for example, attachment of inks on the material. If you have multi-layer, I mean, how are they behaving? And I mean, it's all talking. And I think this kind of projects where you have people in the value chain involved can be already a great help, but don't stay there. Yes, I mean, look actively around and look outside your comfort zone to see if you can identify really winning applications. Yeah, what are we currently doing? So we are finalizing now an ISO certified LCA together with Nova, what I said already. We do quite some upscaling with partners of the different demonstrators. You might have seen that earlier this week we disclosed some conditional offtake agreements, and yeah, certainly with those partners in the upcoming time, we will really prove those demonstrators at bigger scale and bigger quantities. I already mentioned we are starting now the EPC phase, and as well we will continuously working on additional offtake agreements. I mean, I think that is something what should be always high on the agenda. And then in the end, we certainly also will intensify our dissemination activities. So as a last slide to finalize this presentation, I think the project preference is really on track to engineer and build the first of a kind FDCA flagship plant. The initial results of the materials and the end products are very promising. Also, the interim results of the environmental performance of the developed products show also a clear benefit of PEF above PET. And maybe also there, one last remark for other people. I mean, I would say don't do those kind of environmental performances. Certainly, if you have a unique molecule, don't do them on a chemical level, but really do it on an application level in an cradle to grave kind of evaluation, because I think at that moment you can really much better show the benefits, or at least that's our experience, compared that if you would really do an direct comparison of PET versus PEF, for example. Because I mean you make different packaging solutions, and that will really give you a completely different environmental performance. I gave my email address, so if there are any questions which I cannot answer now in the time left, I mean, please give me an email and I will come back to you. Okay, I think this is the final one of my presentation, so thank you for your attention, and I will be open to answer any questions you might have.
Thank you a lot, Ed. Very interesting. We are a bit over time, but I will ask you 2 questions. And the other ones maybe can be answered later in the big discussion at the end. Martin Dubois asks, thank you for the interesting presentation on PEF and Avantium. You mentioned that it is proven fit with existing sorting and recycling facilities. Actually, I had understood that PEF created issues for the PET recycling. Can you comment on this?
I don't know actually where that is coming from, because I mean that is actually not the case, because we have permission from the European PET bottle platform, the EPBP, to have 5% PEF in the PET recycle stream, and actually PEF improves the recyclability of PET, because, for example, it slows down the crystallization rate of PET. But what we do see is quite often that people are not completely well informed, and think that PEF, for example, is very similar to PLA, what is known to create some problems. No, and I think we can discuss that further also offline, but we have the technical data to show that both on a property point of view as well as a color point of view, I mean, there is no issue with bringing PEF in the PET recycle stream.
Thank you. And Sandra Miedl asks or states, amazing material. Do you think it is feasible for the European industries to have a resource independence of the raw material needed to produce FDCA?
Yeah, certainly. I mean, we have to see this in context. Yes, I mean, to start with, I mean, I think this is really a chance for Europe. I mean, PEF, but also other bio-based polymers to create an own position, for example, against China in the production of essential materials what we need to keep our economy going. And if you look at the amount of material what is needed, and then the amounts are really very minimal compared to what you are using already in the biofuels area. So if we assume that on the longer term we will move completely away from biofuels and going completely electrified, I mean, globally now already 80 million tons of ethanol is produced from biomass. So I mean, more or less you can make the same amount of biopolymers from that amount. So that is already a substantial part of the total amount of biopolymers we are now using globally. So both in Europe as well as globally, if we redirect over time the biomass from fuels to materials, we have already, without having major expansions to the land use for biomaterials, already enough material for enough feedstock for biomaterials. Not to mention, another thing is that if we are reducing a bit of our meat consumption, etc., but also will free up quite a bit of biomass. And so I think yes, to make a long answer short.
Okay, that's true. Thank you, Ed, and I hope that you or Claire can stay until the end so that the other questions can still be answered after Simona's presentation.
Yeah, I will do so.
So now we are hearing Simona Neri. She's a project and innovation manager at Iris Technology in Spain, and she is talking about the polybioskin project.
Okay, can you hear and see my presentation properly?
Everything perfect.
Okay, so good afternoon, everybody, and thanks a lot for the invitation. I hope to keep you entertained in this last presentation with the results of Polybioskin project. I am Simona Neri, and I'm Project and Innovation Manager at Iris Technology Solutions, but I'm here today as coordinator of Polybioskin. So Polybioskin was a 3-year project that received 4 million fundings from BBI, and the consortium was composed by 12 partners coming from 7 different countries. During the COVID, we experienced the extension of the project of 3 months, and we successfully ended it at the end of 2020. So just a brief overview about the context of the project. In Polybioskin, we target 3 main sectors: sanitary, cosmetic, and biomedical one. These 3 sectors deals with large consumption, but at the same time, added value production of materials that are mainly made on fossil-based sources. In Polybioskin, even if there are many researches that already prove that there are formulations of biodegradable materials that can be used for these specific sectors, there is still the need to find products with high performances and functionalities that can really target the needs of the market. In Polybioskin, we want to produce 3 different prototypes. For the personal care sector, we are going to produce 2 different parts of a diaper. For the cosmetic one, the goal is a beauty mask, and for the biomedical, a wound dressing. In Polybioskin, we decided to focus on 2 main different family of biopolymers, biopolyesters like PHAs and PLA, and polysaccharides, cellulose, chitosan, and pullulan. So as I was mentioned before, I would like you to focus especially on 2 main points here, because here we want to develop something that goes in contact with the skin. So we need to have materials that, apart from being bio-based and biodegradable, they must be biocompatible. So this was the first statement we made at the proposal stage, that we wanted something that was biodegradable, bio-based, and biocompatible. So here you can see our first prototype. During the project, we focus mainly on 2 different parts of the diaper. The first one is the top sheet, that is the layer that goes directly in contact with the skin. And we formulated a PLA based material that was then embedded with some specific active compounds, because we wanted also to provide some specific functionalities to the material. The idea was to have antimicrobial and antioxidant properties. We achieved them thanks to the use of nanocapsules made of chitin and lignin that were able to encapsulate different kind of active molecules, but in our specific case, we selected glycerulic acid, that is an antioxidant and antimicrobial compound. After that, we moved our attention to the super absorbent polymer. We achieved bio-based and biodegradable polymers, just modifying the cellulose. And in particular, we moved to carboxymethylated cellulose. And in this case, we also demonstrated that you can achieve this polymer from recycled cardboards. That I think is also a nice result. And here you can see that how we produce our super absorbent core. We used a cotton substrate in which we were able to impregnate the super absorbent polymer. Regarding the beauty mask, we decided to follow two different strategies. The first one was to replace somehow the most commonly used beauty mask. So we decided to have a film that went directly in contact with the skin, and we produced it with the formulated PLA material, and we produce it in two different ways. The first one through the use of flat die extrusion, and the second one with compression molding. As you can see, in the first case, the film looks much better in terms of homogeneity of the formulation. But after a consumer perception analysis, we understood that most of the clients prefer the second one because this unhomogeneous material looked much more green for their perception. On the other side, we wanted also to study another possibility for the beauty mask, and we decided to move to a water-soluble beauty mask. So here we use the technology, the electrospinning as a technology, and we performed our final prototype using a carbohydrate that is fully soluble in water. And here you can see I was pushing to be the first user of this beauty mask. The good point here is that, first of all, you do not have to use any organic solvent during the production, but on the other side, you have also something that is soluble in water. And as a polymer was also fully biodegradable. So you do not have this material as a waste. And then here you have the wound dressing. Here I'm showing the design of the prototype that is made of a substrate of chitosan, in which then we electrospoon PHAs that in order to have a layer that goes in contact directly with the skin. And then we embed our chitin lignin capsules on the surface in order to provide the antimicrobial and antioxidant properties. Here I would like to show you also the technology that we use in our project. It is provided by a French partner in the consortium, and it is called dry powder impregnation. With this technology, you can embed powders on the surface of some specific substrate. And in this way, you avoid completely the use of solvents. So here, just to conclude, we wanted to finalize the project, just carrying out a comparison between this scenario, a current scenario, and the one proposed by Bioskin in terms of end of life. Currently, the top sheet and the super absorbent polymer are, in general, all the diapers are landfilled or incinerated, and they are fully fossil-based. And in our scenario, what did we decide? Obviously, our first option is to have something that is compostable. So you can just separate it and somehow biodegrade it. We also get in touch with Embrace, that is another project that dedicated the research to the personal care and diapers more in concrete. And they are also considering the recycling of these materials. So it's something that should be also put in place in order to see if it's possible also with these specific different materials we are developing. Regarding the beauty mask, currently most of them are made of cotton and are usually landfilled. And in Polybioskin, we develop a polysaccharide-based beauty mask that is completely water soluble, and it is just poured out when you are washing your face. The polymer is biodegradable, so we do not see any huge problem here. And finally, regarding the wound dressing, currently there are many different kind of materials used for this specific purpose, and they are made of many different materials, and usually they are landfilled or incinerated also because they got in touch with human fluids. In this specific case, we suggest to have composting or anaerobic digestion instead of recycling, even if in the case it is needed, can be also considered. So here you get my contact. You can get in touch with me in the case you have any question, but you can also find me in LinkedIn. And something that I don't know if it's possible, I would like to share. During our project, we publish a book with all of most of the papers we have published in Polybioskin. So if you are interested in getting it, I will just put in the chat. So you can at least have a more scientific insight related to all the materials we have developed there. And thanks a lot for your attention.
Simona, very interesting. You really got me interested in the last presentation. And you were really fast.
Yeah.
Still would have some time, but now we can go to the questions. Timothy Abraham asks, what is the water-soluble polysaccharide that was used for the masks?
Yeah, that's actually something that I avoided to mention because it's a pure polysaccharide, so we do not have any formulation behind, so it's just somehow kept secret in the project because of IP rights.
Yeah. Okay. So there's no other question here. But yeah, I think we can go to the final discussion and see whether you have some questions from speaker to speaker, or whether we maybe answer the questions about the last presentation about preference. So Simona, didn't you ask whether you can place a question in the Q&A?
Yeah, I had a question for María.
Mm-hmm. Yes.
Because you were saying that you used cold plasma for the modification of the surfaces.
Yes.
And I was just wondering, which is the how do you functionalize then the surface after the application of the plasma?
We use gases to control the plasma, but also we have proceeded with different chemical linking, also for facilitating linkage between the lipopeptides and the surface. and we assessed this, but I can put you in contact with the University of Fribourg, who is doing this research, and then for more details application. Yeah, I see that you have introduced the process that an alternative process in order to establish also the linkage, no?
Yeah, we have been working too with plasma, cold plasma in our different products, because indeed we wanted to apply somehow our nano coating. Then we moved to the dry powder impregnation because it looked better at the end. But yeah, we started looking at plasma as a potential technology, but it didn't work really well actually. That's why I was asking which was your function.
Yeah. We have had a good result, and up to now we proceed forward with this.
Okay, thanks a lot.
Simona, we have another question for you, I think, from Jimena Buri. Do you have any problems with the drying processes of polysaccharides? And he or she assumes that it's cellulose and asks if the cellulose is bacterial or vegetal, and how you do the drying.
Okay, it is not cellulose, and yeah, we do not have any problem because it comes from the electrospinning technology. So you have already the filament that comes out from the needle, and so you do not have to evaporate anything.
Okay. Maria, do you have any suggestions how to proceed? Should we just answer the preference questions that are still open?
Yeah, I think so, that it's probably Ed can answer the questions.
Okay, so to Claire and Ed, has PEF a similar polarity as PET?
Yeah, similar, but a little bit higher, because I mean, PEF contains a bit more oxygen than PET.
And what is the cost difference between PET and PEF?
That's a good question. But I mean, that depends really on scale, and it depends on, in the end, on the application. So if you, it depends on a lot of things. For example, if you make a product that is recyclable and your earlier product is not recyclable, then that can have additional benefits in it. So just thinking about the cost in itself is not a fair comparison. But at the same time, I mean, people should also be aware that initially, I mean, it is a couple of magnitudes more expensive than PET. Certainly because at the moment, PET certainly prices are rising a bit, but I mean, it was very cheap also because of the really low oil prices. But what I said initially, yes, I mean, we are really looking to those kind of applications where we are not really replacing PET, but more we're working quite often together with PET, or replacing other packaging solutions or materials. And so because in the property spectrum, we are above PET. And we are not a replacement of PET, but we are an improvement of PET.
When do you think the flagship plant will be in operation?
So the startup of the plant will be mid-23. So so then we will slowly ramp up the production, and the first materials will be coming on the market in the beginning of 24. I think that is I think a quite normal kind of. I mean, if you you build bigger plants, and quite often construction time is 2 years. And before you can start construction, of course, you have to do what is called front-end engineering and design, and you need all the permits in place, etc., etc. So the whole trajectory is quite a time constraint.
Yeah. Paco Varela says, "Dear Ed, nice presentation. Which are the benefits of using PEF in toy Lego products?"
The benefit, I mean, it's a good question, because certainly, I mean, if you know that the major building block of Lego is ABS, but and that is certainly for the Lego application a kind of perfect material. But Lego really made a statement that they want to go renewable, and also said get rid of let's say compounds such as styrene in longer term. And so therefore we are developing to get a material what resembles very much the ABS material as one example. So it's really fulfilling the policies of Lego in going sustainable.
Yeah. Someone wants to know whether your products are commercially available on the market.
Not yet. So because we have a pilot plant where we produce tons of material, and but they are used together with partners to test the material at a bigger scale and in pre-commercial conditions.
Mm-hmm. Yeah, I have a question to all of you. I'm just wondering whether you think that it might be possible in the future that states will ask to pay how do you call it?
Green premium?
To make the products from fossil resources more expensive, to regulate the market in the direction of the renewable resources. Do you think this will come?
Yeah, I think it will come. The big question is really, should we do it on a European level or should we do it on a national level? I think on a national level, I mean, we see already some small incentives. On the European level, it's still a bit unclear where we are going. But I do think, I mean, that if you are not making it also financially more interesting for partners to move, that it will be a very slow transition, because yeah, you know that that the current businesses are so optimized, etc., and are so cost effective that it is very difficult for a new player on the market to really get traction. Yes, I mean, we are now all happy that PLA is growing, but I mean it's still very small compared to all the other plastics, and at the same time it has been on the market already. Yeah, I mean commercially already more than 30 years. So I mean, if for the new incentives it goes at the same speed, and then we won't see a real transition. And so we need yeah, or carrots or sticks, or maybe both.
Does anyone else want to comment?
In our case, we are facing food waste that means that we think that if we can demonstrate that we can increase food cell life and decreasing the food that is wasted, and monitoring with sensor, with bioplastic, because you can through the food waste together with the plastic that is compostable and then goes to all the food waste could be reused in some way. I agree that recyclability is very important when you can easily separate the food waste to the plastic, but also it's important when you have residues of food with the packaging to go to compostability in order to be reused. But if with the smart biopackaging we can increase food cell life in a big proportion, and monitoring, for example, with the gases inside the packaging, I think that we can have a huge benefit in terms of cost that will guarantee the introduction of the bio-based packaging within the market.
Yeah, if I may add something else, is just to comment a little bit that regarding the prices and the polymers, we are really living in a strange moment due to this COVID crisis and this pandemic and the different lockdowns and how countries worldwide, in a worldwide level, are managing all this situation. But it is true that there is a lack of building blocks, of monomers, of metals, of different materials, and that we are now seeing increases in prices on conventional commodities, polymers, such as the PVC, polyolefins, and so on, that in these 3 months of this 2021 year has increased in more than double the price, even 3 times more price we are paying. And this was something unbelievable and unexpected last year. So somehow the prices from these oil-based materials are increasing. Little by little, these bio-based materials, the prices of production are decreasing somehow. So I guess that in the end, we will get a balance. And on the other hand, we see these regulations from Europe now trying to push the situations and the use of the materials to this bio-based circular economy. So somehow they are pushing also recyclability. But there will be also some room for some applications, such, for example, the packaging that was María mentioning for compostability also. So I think that we will find this balance in the coming years. It's not going to be that much, probably a matter of price for many applications, but a matter of reaching these functionalities and then try to make them recyclability and functional at the same time. So I think we are living in a strange moment, and we will see the consequences in the coming year.
Yeah, I'm sorry, but I still have to disagree a little bit with you, Lidia. I mean, I think what we have seen is that the volatility of the oil price in the past couple of years, I mean, really makes a lot of people very nervous. And I mean, actually, if you have a constant price, even if it is relatively low, it's better to work with than if it goes up and down in very drastic terms. Because, I mean, we have seen it, for example, in the plant bottle, where we used BioMAG, monoethylene glycol, as one of the components for polyester. And yeah, basically the reduction in the fossil prices really made the premium what should be paid to the bio-based yeah, not too high. And so basically a lot of parties who were active in that market dropped out again, because basically they were making huge losses. And I think, yeah, I mean, we will see rising oil prices, but I mean, I think companies and investors, etc., wants to see a cushion also, that if the oil price goes down, that they are not bankrupt immediately. And I think we have seen that now in the last couple of years too often. And yeah, we need something there.
Sure, I agree with that as well.
Yeah, and one other thing, I think what we also see is that a lot of people still don't put their money where their mouth is. Certainly in the financial and investor world, etc. I mean, they all really have big words about sustainability and transition and the future, etc. But in the end, short-term returns on investment are quite often still the key aspect where people decide on if they invest or not. And yeah, I think that we see that all over the place, both in banks and in pension funds, etc., etc. So, I mean, in that respect, yeah, sometimes I'm really jealous on the amount of money what was made available now in this COVID crisis, and how slowly things are going. In the end, the bigger transition is really coming to a circular society, and how hesitant we are really to invest there compared to how easy we can make the investment in keeping the current society afloat.
From my point of view, it is also very important how to address the consumer's needs, how to train the consumers to give the importance to recycling, because recycling will depend on them, and also to have a mentality to go to more, let's say compostability or recyclability, depends on the use of the components, but to have people engaged in the future of Europe, and in order to have more sustainable solutions to be used in the future. And this will take time, but it's important to start also from this training, or for and taking into account their needs. For example, in Smart project, we have a consumer panel in order to give feedback of those packaging that we are developing, in order to get their feeling, and try to get their input also for future developments.
Okay, from my point of view, it's true that we, because as you could see all today, that we had made a lot of advance in the technical part, in the different applications. So I think that we have good possibilities to implement these projects these projects, these ideas, these products, these materials in the market. But of course, we need some facts in the regulation part, for sure, because as mentioned, it is very difficult to fit with all the already established economy based on the fossil based materials. I think that yes, the product regulation is key here, and also in some specific aspects. For example, because we, for example, in AFTERLIFE, we are dealing with the production of some food packaging products based on the PHA, but we are using resize for the production of the PHA. So the connection of resize source with the final food packaging material is something that is that it not exists in the regulation today, and something that should be included there. So yeah, thank you.
Maybe a question also to the rest of the panel. Yes, I mean, we see two things what is happening. I mean, one, that the requirements we face with a new polymer are even higher than for the incumbent polymer. that is both on the purity aspects, so how many impurities are allowed in PEF compared in PET, then the requirements for PEF are higher. And because they want to go that direction, Europe, but they think it is easier to give this requirement already on a new polymer, what is not on the market yet, than on an established polymer. But that really makes it much more difficult to enter the market, or more, it makes it again more expensive. The other thing is really on for example, also on the wastewater requirements that we face stricter rules than the incumbent ones. And I think also if we, what is interesting also to see what is happening in the recycling part is really how are we going to tackle the impurities which are in recycled materials, and how are we going to monitor them? I mean, we have some experience in the paper recycling, but I mean, we also know that a lot of recycled paper is not allowed in food contact. And while if we look at plastic recycling, we really want to go to the so-called bottle-to-bottle recycling, and at the same time do that sustainable and preferably not everything by chemical recycling. So I think those three things, I mean, there are different things, but I mean, are all, the first two are really making it more difficult for new processes to enter the market, because people want to really make it a golden entry, that everything is better than what it was in the past. And the other thing is really regarding recyclability. I think that might actually be a opportunity for bio-based, because I think also on the recycled materials, I mean, we will see much stricter regulations than what are in place now, because of what do we do with metals which are recycled, etc., and contaminating the recycle streams. Any thoughts from your side on this?
Yes, I think that for recyclability, very important issue is how to use secondary materials. If we have to find out application for secondary materials that have enough performance in order to be used. If we don't find the market for secondary materials, then we will not have the trust of consumers, because consumers will not like to reduce the performance of the products that they are using. Then it is really important to work in parallel in recycling and upgrading the secondary materials in order to guarantee that performance of the product and the process can be controlled in a way that it can assure full performance for end users and customers.
I can add something here. In polybioreskin, we didn't tackle this problem because at the beginning we were thinking about a biodegradable material instead of recyclable one. But to tackle this issue, we are also trying to develop some specific technology in order to sort the new materials that are formulated specifically in polybioreskin, but also in other projects that have similar formulation, in order to be able at least to separate them from the normal waste, because we do not really know where this material will go, especially for the sector we have targeted until now. So we try to find new technology, photonics-based technology, to sort the materials out.
We in Techniker are working also in this field. This can be further collaboration on that.
Yeah, like black plastics or metallized one, or in terms of impurity in our company, we develop monitoring solution. So I mean, depending on the the quantity and the typology of contaminants, we also try to follow how is the situation after the recyclability.
I'm also involved in a project called Recreates, and they seem to be able to sort all the plastics, also the black plastics, and with water. And they want to scale up their technology or make it possible to use it in different countries. They are now in Great Britain, I think, and yeah, this will be also an interesting project that's not yet started. But I also think that sorting the materials will get better, and this issue will maybe be solved from the two sides, from product development, but also from sorting technology improvements. I have another question for you that I'm asking myself. When you say that you want to make products that are biodegradable, are you also do you just want to are you just focusing on that the product will be degraded, or are you also researching what are whether the degraded molecules have an impact on the nature where they maybe end up?
We carried out, the test of biodegradability based on the EN 13432 in order to confirm that at least they are compostable. Obviously, in the case of PLA, they are industrial compostable, but then we also try to use different kind of material. Actually, in polybiochemistry, we have many different ones, and I would say that most of them we were able to achieve the biodegradability. In a few of them, there is still a window of improvement. I didn't mention that we are research and innovation action, so our TRL was pretty low, was 6. I would say that we reached at the end of the project even a higher TRL, but still, there is a way to improve these materials and find,
And do you also have to do ecotoxicology tests?
No, we didn't. We actually we made many in vitro tests in order to confirm the biocompatibility, so for the skin application. And then something that I didn't mention before, we also carried out the in vivo test on just for the beauty mask. So we had, even with the COVID, many people attended. I don't know why, and I'm really grateful for that. And we were able to see that at the end, this beauty mask somehow improved the hydration of the skin, so you feel better. But we didn't know the part of the ecotoxicity. We skipped it. It was mainly focused on studying how these new biomaterials are behaving when in contact with the skin.
In our case, in BioSmart project, we carry out the biodegradability also for compostability, but also ecotoxicity and water biodegradability. Then in order to take into account the effect also to the environment, we carry it out in parallel, but I fully understand that in the other project that is more for health, it is a lot of tests related with health issues in vivo test, and takes a lot of effort. But in our case, yes, since we were thinking also in the possibility that the packaging goes to the environment, we carry out this type of tests in order to assure the environmental impact as well.
María, may I ask you, when you do this test about biodegradability in water, Are you doing any difference to take into consideration marine water, inland water?
Yes, there are two type of tests. One is for marine water, and the other is for okay, I say do okay for normal water, but yes, we yes making water, not in marine water. In this case, we can do the both tests, but due to the economic limitation of our work, we do this in marine in normal water. But if I write the project now, I suggest to take both in the future.
Thank you.
María, actually, it was my question too, because the degradation in seawater is something that is something tricky. For example, in the case of some biopolymers that can be biodegradable in some conditions in seawater, they have a lot of problems to be biodegradable. In the case of AFTERLIFE project, sorry, we also tackle the issue of the biodegradability, the compostability, and the recyclability for sure of the polymer, because sometimes it seems that for the biodegradable polymers was not necessary to the recyclability, but in fact it's quite necessary, because we must take into account that we need some feedstock and energy to produce the polymer. So it's something that should be assessed too, for sure.
Okay, so if no one has any question anymore, I think we can end.
Freya, I think that there is a question for Simona, but I'm not sure.
Yeah, I saw it. Maybe we can ask Simona, but there's a question for you. Polybioskin sanitary pads, are they available in the markets?
No, actually, the diaper is the less developed prototype, because we are still missing the rubbers and the adhesives. We have been able to develop top sheet, back sheet, and the super absorbent core, but you know, the diaper is a bit complex. And so, yeah, the company that is involved in the production of this diaper is looking for new materials and also somehow, we'll say, new projects in order to proceed with that.
Okay, thank you. Yeah, then I want to say thank you all for your time and for your effort. It was really interesting, and I hope for the participants too. And if you all agree, I will share your presentations and the recording officially, so for everyone. And I will put the video on YouTube if it's okay.
Yeah, it's okay. Thank
Yes,
you.
yes, it's okay.
I think some of you wanted to share your email address with the participants, and if you want to, you can write me an email, and I will include your address in the follow-up email that I will write them, so that they can contact you in case of any questions. Or someone contacted me also because he is looking for a business opportunity or a connection. He is looking for a material. So yeah, just in case you want to share your email, just contact me.
Perfect. Yeah.
Yeah. And did I wanted to say something else? No, I didn't. Okay. Thank you a lot.
Thank you very
Yes, thank
much
you
for
Thank you very much.
this.
Thank you very much. Bye bye.
Bye.
Bye-bye.
Have a nice day.